will get in here. We have exam 1 coming up on Tuesday next week. And by the way, you'll have SI, according to the schedule, at 9 o'clock Monday, and that's going to be really good strategy to hit that SI if you can, from 9 until 9:50. And then the SI review is a little bit longer, and she'll be setting one up before each midterm. And that'll start at 3:50, but it's in Nicholson, but I think it's 108, okay? And we announced that on the previous lecture. But that'll start at 3:30, and I think it'll go till 5, so a little bit longer. And during finals week, they'll have a big, ginormous review session in the student union in the ballroom, usually is where they have that. So that works pretty good. We're going to have some homework this weekend. In addition, you know what? I forgot to make a slide about it, but let me verbally announce the Chapter 2 mini review is supposed to give you 7 attempts. And it gives me 7 attempts. Well, I've done like 4 attempts on it, just messing around with it and double checking and stuff. But as I understand, it only lets you guys take one. Does anybody take more than 1 attempt? You got more than 1? What's that? Oh, review, and then it lets you take it again? Oh, so maybe that's the ticket. All right, so hit the review button, and that'll, so then you review. Yeah. Oh, so go back into the chapter, and then go to the bottom of the chapter, and then click that, and you could do it. How many attempts have you done? Okay. All right, so maybe that's because I set everybody to 7 attempts. And, the thing is, my software works a little differently than your guys because I'm an administrator. But anyway, so hopefully that'll work. And if it's not, I put in a request to the coordinator for the textbook, and hopefully they'll iron that out before too long. Otherwise, go for it. Go back into the chapter and then work your way through. A few more comments about Exam 1 procedures. And I want to re-emphasize and reinforce some of the stuff that we talked about last time. And that is to be on time. And if the better you can be here, now you guys can come in here at 8 o'clock. I was here today at 7:12 a.m. And you just, so if you want to come and study and get ready at 7:15 or whatnot, 8:15, you just come on in, all right? Now, you're going to have to be ready to sit in a slightly different order because everybody in here right now in first hour, you guys are all kind of hodgepodge around here. We're going to space you out evenly, and there's going to be plenty of seating and stuff, and we'll try to do that. And I'll have a little slide at the beginning up here on display showing you how to get seated and stuff. That's why I was asking about the number of seats in each row, because you guys are a fairly smallish section, so we can give you guys plenty of elbow room. Unlike the other guys, they're going to be in here like a sardine can. So anyways, be here ready to go, and you'll have, the faster we can get started, the more time you'll have, so above 60 minutes. And 60 minutes should be fine, but it's always nice to have a little more. So you might have 64, 65 minutes, something like that. The other thing I want to mention is if you're here, like 1 minute late, just come down to the front and we'll get you started. But if you're like 30 minutes late, you probably won't be able to take the test because the rule is that after the first student hands in the test and is out the back door, nobody else can take the test. Nobody else can start it. All right, so just try to be here on time, and everything will be good. Okay, there's a few students that are going to be over in SAS, and just instead of coming here, report to SAS. You'll do the Scantron as usual, but then the clicker items will actually be written on the test, so you won't need your clicker on Tuesday next week. I mean, if you have it, it's not a problem, but you'll write your answers on the test, and then I will grade it personally by hand, the old-fashioned way, with a red ink pen. So kind of a little throwback action there. But anyways, that works good, and you guys will Scantrons as normal. Again, no cell phone for any reason. So make sure you have it. I mean, if you get really nervous about calculations, and we'll have a few calculations on exam 1. You know, it's not going to be all calculations, of course. It's going to be mostly concepts, true, false, multiple choice, matching. You know, the equations will be matching, and stuff like that. And then some clicker questions usually those are calculations or some kind of a short answer to, you know, like a word to type in. But most of the test is going to be, you know, multiple choice type stuff. All right. But no cell phone for any reason, and we'll be watching. So just get a regular calculator. Bring your iClicker, of course, and a Scantron, the raspberry colored one that you can get at the SGA office in the second floor of the. Is it second floor? Student Union? Yeah. You get one of those every day. So go over there at 8 on Tuesday, get one, and then report here at 8:01. And we'll take the test at 9:01, hopefully. Pencil and eraser, make them a good one, and then your calculator. All right. Now, I have some iClicker questions. Let's do the first one. Turn your clicker on. If this is your first day, Juan Rojas, are you here today? Or last name Rojas? I think it's not here. Okay. If you haven't used it yet, press and hold the power button for 2 seconds, and then press DD, and you'll get the Go Nitro message, and you'll be ready to click. Now we got a bunch of clicking questions. Uh-oh! I already outlined the correct answer. Okay, go ahead and click in the right answer. I'm going to have to correct this for the second class. Oh, Lordy. See, what I do is I write the question, then I put in a little box to indicate the correct answer, and then I animate the correct answer box, unless I forget to. So go ahead and vote for, you better get it right. And I'll mark that one right. So yeah, the coverage today is on exam 1 is introduction. So just read the introduction, reread chapter 1, reread chapter 2, and as much of chapter 3 as we cover in lecture today. Now, I have a fairly good idea how far we're going to get, so I'll talk about that before we take off. All right, so here's our main topic for today, Newton's laws of motion in chapter 3. And we won't get all the way through chapter 3. For instance, chapter 3, section 8 on universal gravitation. We won't be talking about that today. We'll be talking about that next Thursday. And we'll be talking about chapter 3, I think it's section 6 on uniform circular motion. We'll be talking about that next week. But quite a bit of chapter 3. Now, we've already talked about the law of inertia. That's Newton's first law. Every object retains its state of rest or its state of uniform straight line motion unless acted upon by an unbalanced force. Now, that's the idea that Galileo, that's the hypothetical frictionless horizontal plane that Galileo was thinking about. So here's an example of, how the first law can be applied. Think of an apple up in an apple tree. In fact, think of the famous apple, Newton's apple. And Newton's apple tree, the one that fell on his head and inspired him to develop the law of universal gravitation. Hold on, I'm tangled up in my cables here. Hold on a second. Okay, that's good. So the apple tree, so an apple up there in the apple tree is just kind of sitting there, and it's got a pair of balanced forces. So the stem attached above the apple is pulling upward, all right? And the earth is pulling downward with the force of gravity, and those two forces balance if it's at rest, okay? So, but if the stem weakens, and eventually the stem will weaken, it'll dry out and it'll get a little brittle, and then a little gust of wind will break the stem, and down she goes. Okay, and so the balance fails, and down it falls. All right, so that's one way of thinking about the first law. That, in other words, you're talking about either no forces or, which is really an idealization, but most of the time in the physical universe, we're talking about balanced forces, or maybe unbalanced if it fails. And Newton's second law is about unbalanced forces. Anyways, here's another way to think about Newton's first law. In terms of, as the textbook goes into, the shuttle bus, the UCF shuttle bus. If you're standing in the aisle of the shuttle bus, and you're just standing there, and the shuttle bus is at rest, or the shuttle bus is cruising down a smooth road, flat road, at 25 miles an hour, you can stand in the aisle and you don't have to hold on to anything. But as soon as he speeds up, forward direction, you're going to, you don't even think about it, but this is what happens. You brace, he speeds up, you got to brace yourself, because you're going to be tossed back. Okay, that's Newton's first law of motion, the law of inertia. If he turns to the right, he's going straight, 25 miles an hour, and decides, all right, I'm going to take this curve, down the Research Park or wherever it is, at 25, he's going to keep the same speed, but now he's turning a little bit to the right. You're going to have to brace yourself that way, because you're going to get thrown to the left, all right? And you don't even think about it when you're doing it, but I guarantee when you're in your car and you're taking a turn, you kind of brace yourself a little bit, all right? So the bus moves forward, you lurch backwards, or you appear to lurch backwards. Because you're not, and the reason for that is you're not, like the seats are all, bolted down to the floor, and the floor is bolted to the frame, and the frame is bolted to the transmission and the wheels and everything. So they all move the same way, but you don't. Now, if it turns right, you bump your left hip, because you're going to be thrown off to the left a little bit. All right? So, and this is what you do normally. If you're in the aisle, it's a crowded bus, which I understand that sometimes the bus, in some of the outer shuttle buses like Route 1 and stuff, this time of day they're so crowded that they won't take anybody at some of the last stops before getting to UCF. I've heard that, which is kind of bad. But anyway, so you're in the aisle, and you're going to normally do that. That's why they have all those bars and stuff. The seat, and the seats have little handles that you can grab a hold of, And even in a car, a lot of cars you'll see, like a little grip strap for the passenger anyways. The driver's got the steering wheel. So, if you're, the steering wheel is going to do most of your stabilization if you're the driver. But if you're a passenger, sometimes you see a little strap or a little, kind of a little handle that's molded into the side of the passenger door or something like that. When I was a kid, they sometimes had straps that were like above the door and that hung down, and you could reach up and grab, like on the subway and stuff. And but anyways, you just do that normally. And so normally, you know your guts, your stomach knows the law of inertia, because this is what you do normally. You don't even think about it. You're on autopilot. All right. Now, a third way, or a third kind of concept in the first law of motion, the law of inertia, is you can separate the two different motions. If there's no force horizontally, you can just treat that as that component of the motion as just a, like the idealized horizontal frictionless plane. But up and down, we do have gravity, so you can't neglect that. Now, here's a good picture of it. It's a diagram from another textbook. And it shows, number 7, throwing a football to his wide receiver. And look at what I want you to see here in this diagram are the light blue arrows. And the vertical arrows represent, let me get my cursor over here. Okay, these vertical arrows represent the Vy, right? And so here at the midpoint of the arc, he's got a lot of Vy. But over here, when he's getting closer to the top, he's got a little bit less. Because he's on the way up, he's losing upward speed. Now, right here at the top of the motion, where this dotted line is, that's what the point that we would call apogee. Let me spell apogee for you. Apogee. And it's the top of the arc of this football in the air. Now, the people that talk about apogee the most are guys at Mission Control in Houston, because apogee is a word that they use for orbits. It is the point on the orbit around the Earth that is farthest away. Apo means away. Like the apostle is sent, those who are sent away. Apo means away. The opposite of that is a place called perigee. Perigee. GEE stands for Earth. Geo, Earth. Perigee, para means above, or, and in practical terms, it means the closest point of the orbit. Now, if you're on a circular orbit, you don't have a closest and a furthest, because everything's the same distance from the Earth. But most orbits around the Earth are slightly elliptical. Like the space station, I think, is slightly elliptical. And some orbits, as we'll talk about next week, are very elliptical. It just depends. They make the orbit what they want. So perigee is the point of closest approach. Aphelion is the same thing for solar, or for a planet orbiting the sun. And let me spell that one for you. Aphelion. Aphelion. So it's away, apo, from helion, helios, sun. And so on a planet's orbit, or a comet, or an asteroid, the point on its elliptical orbit furthest away is aphelion. Perihelion is the point of closest approach to the sun. Perihelion. Now, don't worry about that vocabulary term, but you'll hear me talk about it from time to time. And apogee is at the top. In our class, we're pretty much going to be talking about apogee, because we're not talking about planets that much. But anyway, it's the top at apogee. What happened to the vertical arrow? There's no vertical arrow. And that's because at apogee, you better make a note of this. At apogee, that's the unique point where, for just an instant of time, it has lost all of its upward speed. You know, the quarterback lofts the ball, and it goes up for a little while, but eventually it loses all its upward speed. Now, horizontally, it's still rotating horizontally. But vertically, at apogee, ding, it's all gone. Now look at this next one. So this is the fourth image of the football in motion. He's starting to get a downward velocity vector, and that's what happens. What goes up must come down, and on the way down, it gets more and more downward, and that is why here in the fifth football image, it's got the longest light blue velocity vector downward. All right, and if you take more strobe photos of it, you can make longer and longer arrows as it gets closer and closer, and then as soon as the wide receiver catches it, of course, then it stops, and then it's just got him carrying the ball down the field and then spiking it for a touchdown and all that kind of stuff. Anyway, so Galileo said, separate these motions. All right, now here's what it means. They're separable. Here's the horizontal motion. There's no such thing as horizontal gravity. So horizontally speaking, the x-coordinate as a function of time, x of t, is equal to its x-coordinate at time t equals 0, that's x of 0, or x subscript I, we sometimes use that notation, plus vi in the x direction times t. Now, you know what? Let me go back to this image here. Look at the horizontal arrows, the horizontal light blue arrows. Those are always in the same direction and always the same size. So the horizontal component of the velocity, Vx, is always the same as Vix, because there's no such thing as horizontal gravity. All right? So this is a distance rectangle. Ding. We know how to do that. Speed times time. Horizontally. But now vertically, you got problem 12 on homework 3. And did you guys see that I made some more availability on that? It's now due next Tuesday at 9 a.m. and you have another 3 attempts. Who was here that was in that study group that asked me about it? Anybody? Yeah, good. You're Diamond. Okay. You saw it. So good. Did that work out for you guys? Okay. Yeah. Anyway, so this is what you got in that one. So look at this. Now this is the free fall equation for the y coordinate. Now this is not a drop distance. Drop distance is just 1/2 gt squared. That's easy. But if you're trying to figure out the coordinate, could be positive or negative, you got to do it this way and much more carefully. So here's your initial position, and we're going to do this in a second on the document cam. Initial position on the y-axis, how high is it? And then here's a distance rectangle, but that ain't all. I mean, if it's lofted up into the air, you have a few meters per second of VIY. But then you've got the action of gravity here, and this is with g equal to negative 9.8 meters per second squared. All right? So that's an accelerated motion, a velocity rectangle, a distance rectangle and a distance triangle. And we can deal with that. We have been dealing with it. You've been doing it on homework 3, homework 3, question 12. Let's do it on document cam. Now, let me pause the YouTube for a second. And now, I have a few more clicker items I want to ask you about. Okay? So here's another clicker question. And this one's also kind of related to the first law. If an object has balanced forces acting on it, it will continue in a straight line at constant velocity. And if not, then you have to go to second law of motion. All right, so this is blue car, moves to the right. Constant speed. Which one of those is correct? Read carefully. And this one you don't accidentally have the correct answer, so you got to think. And of course, you can't select F because this is multiple choice. You can only select through E. But why would you even want to select F? All of the above contains none of the above. So it's kind of a... I actually did that on a test once when I was in grad school. I was writing a test for my astronomy students, and my TA said, you know, I wasn't a doctor at that point. He said, Thomas, I don't think this is a good question because you have all of the above below none of the above. All right, let's see what we got here. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good, 97 votes. Yeah, this is the same thing as saying it has constant speed. Direction is constant, speed is constant, that's constant velocity. And that means let's see what it means. Here's a velocity arrow in red. And, here's a description of it. It might be 10.5 meters per second, that's 20-something miles an hour. Rightward. And so that's a vector statement. Now, when you see me put a little arrow over the top of a symbol, that means I'm talking about the vector, which is represented as an arrow of some length and a direction, some direction. Okay? And forces, accelerations, velocities, and even positions have a vector, okay, or a vector representation. Question?
I'm not sure if my iPad is working because when we did the last quick question and this one, it just says like ready, and then when I press the enter and press send, it's not.
Does it say no base?
No.
Yes?
It's telling me no base as well, but I pressed E as well.
No base means you have to hold the power button down hold it down, until it flashes the rectangle. Go ahead and hold down the power button. Hold the power button down for just a second or two, and then it flashes, and then type in DD.
That's not my problem. I put the answer and it just says ready since I turned it on.
It's not working then. You're gonna have to get a working clicker. Do you have did you get Go Nitro?
Yes.
Okay, so now you can start voting it for, I don't know what to tell you about yours. Maybe switch over here to the front. I don't know. They're radio frequencies, so I mean that shouldn't be too far away. You don't have to aim it at the receiver or anything like that. It's not like a TV remote. A TV remote is infrared. You have to aim it at the TV. But these ones you could do behind the back. Doesn't matter. All kinds of trick shots. Next question. You observe a can of Pepsi on a tabletop and it's at rest. That's a constant speed. Speed equals 0. Which of these 4 sentences is true? Let me start this. Go ahead and vote. Did you get are you going to move or are you going to stay there? I mean, I don't know what to tell you other than that your clicker's not working.
I mean, it says ready. I just don't know.
If you click a letter, does a check mark come up next to it?
Yeah.
Then it's working.
Well, then you got it. Yeah. All right. So you're good. How about you? Did you get a good? All right. Ooh, a little bit of controversy. Okay, 15 seconds. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let me show you what you got here. It's kind of interesting. Now, when I say that there's a controversy, that means there's a bunch of people voting outside the correct answer. All right, and the correct answer is not D. In fact, let's go back to this. The correct answer is B. And here are go ahead and make a sketch or make a note of some kind. Can of Pepsi on the tabletop, there's two forces acting on it. Number one, it's got a weight force. Okay? But because it's at rest, it's not in free fall. So if you were in free fall, then yeah, you got one force acting. You know, you jump out of a plane, pretty much one force acting. Maybe two if you consider air resistance. But we're on tabletop, it's at rest. So what that means is you have downward weight force and you have some upward rigidity force from the table. Okay, so make a note. The rigidity, and this is in the textbook, I go into it in detail. The rigidity force from the table, I mean, you can't make a table out of water. Okay? Unless you're in a science fiction movie. Or unless it's frozen water. But liquid water, you know, it doesn't have any rigidity to it. It has a little bit of buoyancy. You can float stuff on it. But, you know, a can of Pepsi, no way, Jose. All right? So it's got to have some rigidity, and that means that there's got to be some upward push force from the tabletop. All right? And that's what rigidity means. No matter what you put on it, up to the point where the table breaks, you know, you can't get an elephant to put his foot up on here, he'll crush it. But I mean, short of that, you know, if it's a good stout table, it'll have enough pushback no matter what you have. And basically what it is, all the little atoms and molecules in the wood, the plywood, whatever it is, in the plastic, they act like kind of like a trampoline. And you know, when you get on a trampoline, you sink in the trampoline, it stretches the trampoline, but only far enough, Diamond, to the point, you know, you might sink a couple inches, but then you stop because now the trampoline's supporting your weight. Okay? And that's what this is like. Okay? It's like a special trampoline. You can't really see it dipping down the way you can see a trampoline. But yeah, that's what it's doing. That's what we think anyways. That's the way we look at it. Tiffany. It's Tiffany, right? Right.
So what would be an example of an object with an upward force?
You pulling on it. You attaching a string to the top of it and trying to steal the Pepsi, you know, without anybody seeing. All right? You know, and you just think of anything, you know, a pull or a push that you could achieve on the Pepsi. You know, say that there's a little opening underneath the can of Pepsi, and you push on it upward with your fingertip. Okay. So here's your upshot. No delta V, so no acceleration. The initial velocity is 0. All directions, so no acceleration, therefore no unbalanced forces. Now, so that's kind of what the first law is about. How do you handle a situation where you either have no forces or you have balanced forces? Now, second law, what if you do have unbalanced forces? How do you deal with that? Well, let's talk about it. Because if you have unbalanced forces, you're going to accelerate, all right? So what you do is you add up all the forces, you know, all the lefts and rights, and you see how much, if you have more right than you have left, then that's part of your net force. And then you add up all the ups and downs, and all the to's and fro's, and you kind of figure out your force arrow. So if it doesn't balance, like the can of Pepsi, then you've got some leftovers, and that's what you call the net force. Now, here's an example. All right, so think of a basketball, and Dwight Howard and LeBron James are battling for it. So let's say that Dwight Howard pulls to the right with 100 metric units of pull force. Okay, so there's his arrow over there. All right? And LeBron James, weenie that he is, can only manage 80 metric units of force to the left. All right? And what that means is that there's 20 units left over. Dwight Howard can bounce everything that LeBron James can dish out, and 20 units more. And so that's the net force. So we would say that the net force is 20 units. And I'll give you the metric unit of force here in a minute. 20 units to the right. So you would, make a little. So you could replace the upper diagram of a basketball with two forces in opposition with one basketball or even a dot with the net force arrow, because that's the one that's going to cause the acceleration. All right? Now, one thing that's going to happen if Dwight just has a little bit extra, it's effectively going to be still a jump ball. All right? And so one way to encode that or to state that is that the more push, the more net force, the more acceleration you're going to have. So he's 20 newtons, that's pretty good. So he's going to win the battle. All right? All right. And if he has exactly 80, then it's going to be a jump ball. Nobody wins. All right? But Dwight Howard wins this one. So the more push, the more acceleration. So if you give it a big... So this is like Superman versus a little shrimpy first grader. A little shrimpy first grader can push, but Superman, he could really push. All right, so Superman's going to, move something. What does Superman move anyways? He can stop a locomotive with his bare hands. No, he can bend steel with his bare hands. Jump over buildings in a single bound. Superman. The more kilograms of mass you have, the less acceleration. All right? So if you're a little shrimpy first grader and you have a full grocery cart at the store, you're not going to budget very easily. But if you have a little first grader at the grocery store and it's an empty shopping cart, he'll be able to push that around stuff, help his mom. So the more kilograms of mass, the less acceleration. Now what that means is that the acceleration, the formula is going to have mass in the denominator and net force in the numerator. It's going to look like this. There it is. Acceleration, which we can measure with some distance and position and time measurements. It's equal to the ratio of the net force with the mass. Connor?
Don't you have to take in who's pushing the cart for that feature?
Yeah, and who's pushing the cart is encoded in this equation as F net. So Arnold pushing the cart, Arnold Schwarzenegger, he's going to have a bigger F net than a little first grader. The F net for the first grader is going to be like, 1 unit, and Arnold's going to be like 105 units of force. Okay, so that's up there in the numerator. And then the cart, the mass of the grocery cart, like 25 kilograms, that'd be a fairly good load of Cheetos and stuff. That's in the numerator, the mass. So, all right. Now, another way to write that is just to cross multiply, and F net equals MA. If you ask an engineering student, this is the This is the equation that's kind of engraved in their mind. F equals ma. All right. So if you ever see an engineering student working on their homework and you want to burn their butt, just say, oh yeah, okay, F equals ma. And you'll always be right. But they'll think, how did they figure that out? Just by looking at my homework. But you'll always be right, because F equals ma rules the cosmos, especially for engineers. They have it engraved in their mind. Now, here's on the right a list of 3 expressions. The first one's definition of acceleration, delta v over delta t. And Newton's second law, acceleration equals F net over m. Yeah, that's right there. And then second law, F equals ma. Yeah, that's the other version of it. You know, that's good. The acceleration is something that we can measure, and mass is something that we can measure. But I want to modify this second version, F equals ma, and I want to put delta v over delta t into it. All right, so there it is. All right. And this last version is instructive for us because all the things over there on the right are measurable. Kilograms, we can measure that. Acceleration, delta v, yeah, we can get that. You know, I've got to make some measurements, but we can do it. Delta t, yeah, stopwatch, we can get that. Interaction time, elapsed time. So the measurements are time, distance, and mass. And then the calculations are velocities, acceleration. And we can do all that stuff. And if you're hauling something to a stop, you know, like Superman stopping a locomotive, okay, which is like a freight train. You know, so Superman stopping a freight train. The amount of time, that's, you know, the stopping time, that's down there in the denominator. All right, so if Superman wants to stop it instantaneously before the train runs over Lois Lane or something like that, or Perry White, you know, then he's got to have a very small, so he's got to have his ultra toughest stopping force. But if he doesn't have to, you know, stop it, if he has 30 seconds to stop it, then he can, you know, just kind of use his little finger to stop the locomotive. All right. So the more stopping time, the bigger the denominator, smaller force. So that's Superman using his little finger to stop a locomotive. All right. But if he needs a really short stopping time, that means the denominator is going to be smaller, and he's going to have to use, you know, his full bulk of his Superman forces. All right. Now that's kind of a fanciful illustration, Superman and locomotives and all that stuff from comic books and TV. But here's something that you guys do at the gym. If you do any plyometrics, you know, box jumping, you know, one of the things that they'll tell you, well, hopefully somebody did tell you, don't land with your knees locked because it'll really hurt. Give a little bend in your knees when you land, right? And if you do that, you won't like totally tear your knees apart, right? So that's an example of how to think about the stopping time, because when you flex your knees, that means you got a bigger stopping time. That means the net force to stop is going to be easier on your knees, smaller force. All right. Now, I was going to write something here and I forgot, and I went to do something else. Let's talk about measuring. So sorry about that last slide. Anyways, let's talk about how to measure mass. And mass is the quantity. I mean, we've kind of already talked about it, kilograms in the metric system. It's the quantity that encodes inertia. So inertia is a concept. Mass is the numeric quantity. The more mass you have, the more inertia you have. And that means the more mass you have, the more inertia you have, the harder it is to change your dynamical state from rest to 10 meters per second to the right, or from rest to 10 meters per second to the left, or any other speed, or any other delta V. The more mass you have, the harder it is to get in a little bit of delta V. All right? Now, in the metric system, the unit is the kilogram, and actually it's based on the gram. The gram is the mass of 1 cubic centimeter of H2O at I think it's 27 degrees Celsius, something like that. All right? So you take a little tiny container, 1 centimeter, by 1 centimeter by 1 centimeter, a cube, fill it with water, and then put it in your scale. And that'll measure, that's about 1 gram. Go ahead and make a note. 1 gram is about the mass of a paper clip. A regular sized paper clip, not a jumbo paper clip. All right? So what you do is you take your balance, like this balance here, and you put your object in the balance, and then you go to the other side and balance it with some countable number of cubic centimeters of water. I mean, effectively, that's what you're doing. Now, you don't really use water in a balance, but you do use metal weights, and those metal weights, at some point in their history, were compared to something, some other weight that at some point in its history, and on back to a volume of water in Paris, the origin of the metric system. Question?
So does that mean there's such a thing as like potential inertia, or does that mean
No.
me sitting in this chair, I have inertia?
You sitting in that chair, you have inertia simply because you exist. And so many kilograms, so many hydrogens, oxygens, carbons, etc. in your body, and so many protons, electrons, neutrons. And you're all together, and so we say that you have a certain mass. Now, in the metric system, that's going to be so many kilograms. English system we don't use for mass.
So what does inertia exactly mean?
Inertia is the property that opposes changes in the dynamical state, either direction or speed. Okay, the dynamical state.
So it's a force?
No, inertia resists an external force. Okay? All right, so let's think about, here's a countable number of cc's, a liter bottle of water. Okay? So that's about 1,000 cc's, right? And so that's 1,000 grams, 1 kilogram. All right. Now you put your other object in the other side, and whoops, if it's a basketball, it's going to be overbalanced by 1 kilogram. So you take some of the water out and measure what you take out, and that'll allow you to keep count of what's in the balance. And eventually, they'll balance out, and then you'll know, okay, the number of grams of water that I've got, that's how many grams of mass in my basketball. And the basketball, I think, is about 0.6 kilograms. So it's not quite a full kilogram, the way a liter of water is. But anyways, that's what you would do. So anytime you measure the mass of something, it's basically counting cc's of water, except you use, in practical terms, like when you go to the doctor's office and they have that scale that they use, to measure your weight and stuff, that's metal. But you're balancing a given amount of metal that at some point was compared to a bunch of water. So let me ask you a question here, another clicker question. F equals ma. Remember that? Your liter bottle of water has a mass of 1.000 kilograms. It accelerates from your pull force. Okay, so you're putting a pull force on it, and you get 1 meter per second squared of pull. of acceleration, I should say. What's the size of the net pull force? All right. So in other words, what's F equals ma? You know the mass, you know the acceleration. F equals ma. 15 seconds. Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Yeah, most of you got this one right. 1.00 kilogram meter per second squared. F equals ma, a mass times an acceleration. And hey, you guys, that is the official unit of force in the metric system. We call it the Newton. So 1 Newton is a kilogram meter per second squared of push or pull. You can say it this way. A force of 1 Newton accelerates a 1 kilogram object at 1 meter per second squared. All right, so that's how we define the unit. And so the Newton is what we call a derived unit. We don't have an international Newton sitting in some museum in Paris for the metric system. We do have an international meter over there in Paris, and we do have, the international kilogram sitting over there in Paris, but not the international Newton. It's a derived unit. And this is your first use of the law, F equals ma, calculation-wise. Let's do a scary T-Rex, 342 kilograms. Hit the refresh key because we're going to do a calculation now, numeric. Hit refresh, and you should, I think it'll start with 0. Is that what you got? Hit the refresh key, or 1. Okay, starts with 1. Here's your calculation. Calculate the weight force, F equals ma, for a 342 kilogram T-Rex. And your acceleration of gravity. So this is actually F equals mg. And that's the formula for the weight force. F equals mg. So go ahead and do that real quick and talk to your neighbor. And your homework over the weekend, I'll have a few basic questions like this, and you can try it out. Well, so far 2 people have voted, and they're both give it to the nearest newtons. I don't want any decimal points. So some of you, yeah, and round off carefully. Okay, good. I can see you guys. Good. Oop. Raise your hand if you have a skateboard with you today. Okay, great. Okay. All right. All right. Still a few of you have a bad round off, but and it looks like a few of you have got some decimals. Okay, 30 seconds. $20 seconds. $10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, good. Raise your hand if you voted for 3,352. Sweet. All right, there's your answer. Okay. Now the rest of you, if you messed it up, you missed a decimal point or something, yeah, just double check it. Connor.
How is gravity a positive number? I don't understand.
Because we're just asking for a number of newtons. Oh, did you type in a negative?
No, I'm just saying that gravity pulled on the dinosaur, so wouldn't that be?
Yeah, if we were going to write a vector for it, then I would say put in a minus sign for downward.
So how do you know when to add?
You have to read carefully and look at the context. And I'll usually say, if I say the word size or how big, that doesn't ask for the direction. So that would be a speedometer reading or just a drop distance, and you should have to worry about that negative sign. But if I'm asking you what direction or where, then those are tip-offs to the fact that I'm asking something that's directional, and so you have to have minus signs, possibly. And let's talk about the directionality of Newton's second law. Now here's how you do it. The net force on an object is equal to its mass times acceleration. Okay, so that's F equals ma. And it points in the same direction as the acceleration. So the way that you would write that in an equation, the net force with a little arrow over the top equals the mass m times acceleration, and the acceleration has a little arrow over the top. In other words, the two arrows, one for acceleration, free fall acceleration downward, and that means that the net force from free fall is also downward. But if you have a rightward net force, that means your acceleration is rightward. And so you look at the acceleration, and that tells you where the net force is. Now that you may have more than one force acting. The acceleration won't tell you that. It will tell you the net force. Whatever leftover force, it's in the same direction as your acceleration. And that you'll be able to tell. So it can a net force can speed something up, it can slow it down or change its direction. So if you get a force, like in this diagram, this little gold sphere smushing into this Ferrari, kind of from the left and behind, coming in at 45, you're going to get a little bit of a speed change. It's going to go a little faster, and it's going to get a direction change. It's going to go off to the right. All right? And so that's what acceleration can tell you. Your delta V is going to be in the same direction as you get some push from that little gold sphere that's smushing into your Ferrari. Now let's talk for a few minutes about Newton's third law, action and reaction. Two skateboarders. Raise your hand if you have your skateboard. Okay, you and you. Okay, bring them down here fast, and come down to the front. And what we're going to do is a demonstration that you're going to read about in the textbook. No, not you. You. Okay. Put your bag down. I want you to be as light as possible. Okay. So come right up here in the front. And I want you guys to mount up and face each other. And what you're going to be doing is pushing off from each other. So inch a little closer. Okay, and then I want you to go like this. I want you to go patty cake like this, okay? Now don't do anything yet. Okay? But when I say 3, 1, 2, 3, I want you to push off. Okay? Now these two students, very brave students. What's your first name? Logan and Angelica. Okay, now they're different masses. Angelica's a little bit less mass. All right? Ready? 1, 2, 3. Whoa! Angelica's way over here. Right? Because she has less mass. Let's try. Well, let's see if it's switch positions. Do the same thing. switch around. And when I say 3, now let me ask you a question. Angelica got a little bit more motion out of it. So does that mean that she was in contact with Logan a little bit longer than Logan was in contact with her? I mean, after all, she did get pushed further, right? So that means she was in contact longer, right? I heard somebody say no. Who said no? You don't. Is it possible for? What's your name again? Angelica. Is it possible for Angelica to be in contact with Logan than Logan is in contact with her? No, it's going to be the same amount of time. So whatever interaction time, delta T, it's going to be the same for both. All right? Let's do it again. Let's try it again. Okay, patty cake time. Okay. 1, 2, 3. Whoa! All right, do over. Angelica, don't. Logan, whew. He must be Wolverine's little brother. Okay. Okay, ready? 1, 2, 3. And again, Angelica's way over there to the left. All right, let's give those guys a hand. And what we're going to be talking about now for the last few minutes of lecture today is the third law, Newton's third law. And this is a diagram from another textbook of something that we call third law pairs. The two forces, the force of the spacecraft on the astronaut is to the left. So the spacecraft and the astronaut pushes off on the spacecraft, right? So the force of the astronaut on the spacecraft is to the right, and the spacecraft pushes back, just like Logan and Angelica did. All right? And these are called third law pairs. And here's the kicker. The recoil speeds are not the same. All right? Now, we've already done the skateboarder demonstration. Hopefully you took a few notes. And I want to show you something from chapter 3 about another skateboarder interaction. Now this one, because I didn't know, I don't have their mass, I don't have their speeds, so I made up an example of two other skateboarders, Carl and Bob. Now here's Carl's mass, and here's his initial velocity. He's at rest, just like Angelica and Logan were. And let's say that Bob is also at rest, but he's got double the mass. So Carl's a 7th grader and Bob's a full adult. Okay? And so now their interaction, now Sir Isaac Newton said, for every action there's an equal but opposite reaction. So what that means is, whatever force that Carl presses on Bob, Bob presses exactly the same size, but the opposite direction. So let's say that these two skateboarders have an interaction force of 500 newtons. So what that means is, depending on which direction they're going, one will be positive and one will be negative. Now here comes the negative signs, Connor. Let's say that Bob pushing on Carl, B on C, is positive 500 newtons. All right, so that's this. So that's like pushing to the right. And the force of Carl on Bob is same size but left. It's leftward, negative. All right. So Bob is going to get some leftward motion, and Carl's going to get some rightward motion, just like Angelica and Logan. Now this was designed to have nice round numbers. If you measure the mass of Angelica and Logan, they probably come out, like 102 or something like that, 92.5 or something. But these ones are nice. So here's the interaction time. Now, I tried to trick you guys on this. I couldn't do it. They both have the same interaction time. Delta T. Right? So that's the amount of push
And that's a long, actually half a second. I'm sure Logan and Angelica were way less than that. But let's have a, let's just say, okay, they have long arms. Okay, yeah, 48 hundredths of a second. Now, let's figure out the acceleration. We have the force. We have the mass. So let's figure out F equals ma. A equals F over m. So for Carl, the acceleration, 500 divided by his mass, and it's positive, 12.5 meters per second squared. So he gets some acceleration to the right of that magnitude. Now Bob gets negative 500 newtons of push force from Carl, and so he goes flying to the left, but guess what? It's only negative 6.25. Why? Because Bob has more mass, just like Logan. So Logan went to the, went off to the left, but it wasn't quite as spectacular as what Angelica did. All right. Now let's figure out delta V. Delta V is equal to A delta T. And so for Carl, delta V, 12.5 meters per second squared times 0.48, easy peasy, 6.00 meters per second. Now, if you don't want to, hustle and bustle to copy all this stuff, it's all going to be in YouTube in an hour or two. Right? Now, here's Bob, delta V. Now, look at that. Opposite direction, he's still got that minus sign, and a lot less delta V. Now, he started at 0, and he only got 3 meters per second to the left, all right, because he has more mass. So the final velocity states the initial was 0 for both of them because they were at rest, just like Angelica and Logan. So Carl's final velocity, 6.00 meters per second. And Bob's 3.00 meters per second negative to the left. All right, just like Logan. So in this example, Carl is like Angelica, Bob is like Logan. All right? And I want you to take careful look at the net force, or the forces of interaction, and the interaction time. And I have a question for you. Clicker question number, whatever it is. Oh, better hit your refresh key. Hit refresh, because we got a multiple choice question here. So this is their, they both have 500 newtons, plus and minus, and they both have an interaction time of 0.48. So what does that multiply out to? It's constant. One's positive, one's negative, but other than that, it's same size for both. Connor, same size, so that means I'm not really focusing on direction here. So what does that work out to be? Go ahead and vote. Carefully. 500 newtons times 0.48 seconds. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, most of you got it right. 240 Newton seconds. And hey, you guys, a Newton second is the same as kilogram meter per second, and that's a mass times the velocity. Now, I'm going to have to skip over the last few slides here, so we're not going to have a clicker question. But I do want you to look at this equation
It's actually in like the second or third paragraph of section 4.1. It is also the form, this is the impulse equation, force times interaction time equals m delta v. And it is also the form that Sir Isaac Newton thought about his laws of motion. There's a postage stamp with a cool picture of Sir Isaac Newton. It's called the impulse formula. Now, last comment about the exam. And study everything. There's going to be another homework in web courses, and try to get that Chapter 2 mini review in Great Rivers. Our coverage is up to Chapter 3.7, all right, it's in Newton's third law, but, and also like the first 3 paragraphs or so of 4.1, but we skipped over 3.6, and we skipped over 3.8 through 3. Whatever, the rest of Chapter 3. So it went up to 3.5, skipped over 3.6, talked about 3.7, and then skipped over to 4.1, the first couple paragraphs. All right, so there's your coverage in Chapter 2, Chapter 1, and the introduction. Okay, you're dismissed. I'll see you next week. 2 minutes late.